Yeah, it was there. It was there on Friday too. Perfectly good watch. I assume. There's a problem to work on. Care to. Guess I'll turn down the light. Christmas is not on Wednesday. No, not Christmas. Okay. I heard Christmas was on a Wednesday. That's fine. Ah, I see. I'll turn down the light. My favorite part of that. Worst. I mean, so much. Orders. Fine, that's fine. I'll live. So this question's kind of interesting, I think. You can certainly guess at an answer, and there's lots of right answers to this question. There are plenty of matrices that if you multiply them by themselves, you get the zero matrix. One such example is this matrix, 0, 3, 0, 0. If you multiply that matrix by itself, you get, let's take a look, 0 times 0 plus 3 times 0. Yep, that's 0. And 0 times 3 plus 3 times 0. 0 again. And 0 times 0 plus 0 times 0. 0. And yeah, all zeros. But that's kind of not very interesting in that, sure, I just showed an example. But like, how do we kind of figure out a generalized example? Well, here's what we would really do if we were asked this question and didn't just kind of have a good guess already, because you might not. So I'd start off with, well, let's just say that A is a very generic A, B, C, D. We're going to multiply it by itself, A, B, C, D. And we know how to do this. It's going to be the rows of the first matrix dotted with the columns of the second matrix. So first row, first column is A times A plus B times C, or A squared plus BC. And then we have A times B plus B times D. So AB plus BD. And then second row, first column, CA plus CD. And then second row, second column, CB plus D squared. So we have four equations. We have that each of the things, each of these entries needs to equal 0. So our first equation is that A squared plus B times C has to equal 0. Our second equation is A times B plus B times D. I might factor out a B here and say B times A plus D is equal to 0. Our third equation is that I'm going to factor out the C as well. C times A plus D needs to equal 0. And our fourth equation is that CB plus D squared has to equal 0. And I would say that our second and third equation actually give us something to work with. So these equations we can either have B equal to 0 or A plus D equal to 0. And similarly over here, we can have either C equal to 0 or A plus D equal to 0. So let's say we have the first case where B is equal to 0, and let's say any more room here. You still see that right? Yeah. So case 1. If B equals 0, let's see what we're left with. Bless you. Bless you again. So if B equals 0, let's look at equation 1. Well, then we have A squared plus 0 equals 0. If B equals 0, A is going to have to be 0. And then we can also look at equation 4. If B is equal to 0, then we have 0 plus D squared equal to 0. So we're going to get D equal to 0 as well. So this is going to be a matrix kind of like what we had before. I suppose I should look at equation, 3 as well. So then I have equation 3, C times A plus D equal to 0, but A plus D is already going to equal 0. So C can really be anything. And this gives us a solution similar to the one I came up. Why is it always so rumbly in here at this time? That's like, okay, anyway, sorry. So C can be any number. So another solution would be something like 0, 0, any number you want, 0. Again, not super exciting, but kind of interesting. That's very similar to the solution I just mentioned at the beginning, which was 0, 3, 0, 0. Not the same, but similar. The other situation is actually a bit more interesting. So case 2, what about if A plus D is equal to 0? Or in other words, if A is equal to negative D. Well, let's look at our equations. From equation 2, we have that B times A plus D equals 0. So since this part's already equal to 0, B can be anything. Well, at least so far. We don't have any restrictions on B yet. From equation 1, we have A squared plus B times C equals 0. Okay, let's see. What do I want to do with that? Well, I know that A isn't going to be 0 because I already kind of dealt with that situation before. So looking at this, I'm going to say that C, or B times C, is equal to negative A squared, and C is going to equal negative A squared over B. Okay, so it looks like I've kind of got everything together here. Check this out. I'm going to have A here, and then B is just whatever B is. C is negative A squared over B, and we already know that D is equal to negative A. So now just pick an A and a B. You can pick kind of any numbers you want. We can be very unexciting here and pick A equal to 1 and B equal to 1 as well. If we do that, check out the matrix we get. 1, 1, negative 1, negative 1. There's a matrix that you might be surprised that you multiplied it by itself, you get the 0 matrix, but you do. If you multiply this matrix by itself, look at it, what we get. 1, 1 with 1, negative 1 is 1 plus negative 1. Same deal there. Negative 1 times 1, negative 1 is also 0 and also 0. Yep, all zeros. And there's lots of other choices, right? You could let, say, A equal to 1, or sorry, A equal to 2 and B equal to 1, and you would get something like 2, 1, negative 4, positive 2. That may, oh, sorry, negative 4, negative 2. Apologies. That matrix also, if you multiplied it by itself, you get the 0 matrix. Really, all this is just to point out that matrix multiplication is a little bit different than regular number multiplication. You couldn't normally find a number that wasn't 0 that when you multiplied it by itself, you got 0. So matrices kind of have some different multiplicative properties than real numbers did. Okay. And that's all I have there. Let me I have a handout to pass out. I should just do this smart way and pass a bunch to you and a bunch to you. You guys can pass them all back. And there's extras, just put them on the desk and I'll collect them in class. Back forward. And just leave them wherever they get to their full. Everyone has gotten one. Okay, so what we're going to talk about now is kind of modeling with matrices. Let me put these pages to the side here. This is, I think, from section 8.4. Make sure we're all. So, yeah, come on. Let's be careful. So notes on Leslie matrices. Why are they called Leslie matrices? Because the person who used them, his name was Leslie, I'm assuming. But they're really about using a matrix to help us model populations from one year to the next, or more generally, one time interval to the next. So we're basically going to say we have so many of each kind of age class at a particular time, and then we're going to ask how many of each age class do we have next year, or next week, or next whatever iteration of the time interval it is. So let's take a look at what we've got here. We're going to assume a population is divided into 3 age classes at time equal to 0. N sub x of t is going to equal the number of females of age x at time t. So our vector here, n of t, is going to give you all the different ages at particular time t. So the first entry is n0 of t, which is the number of 0-year-old females at this time. N1 of t is the number of 1-year-olds. N2 of t is the number of 2-year-olds at whatever particular time we're looking at. So let's continue the problem. We're going to assume that 20% of 0-year-old females survive to age 1, 70% of 1-year-old females survive to age 2, and all 2-year-olds die. Okay, well, it's like bugs or something, right? It's not people. I mean, it doesn't matter really. So here are the equations, the different equations that are relating this for us. So we're saying 20% of 0-year-olds survive. So 0.2 times the number of 0-year-olds at time t become 1-year-olds next year because 20% of them survive to the next iteration. Similarly, the number of 2-year-olds next year is 0.7 times the number of 1-year-olds this year. And you don't really need to write it, but we could. No, I don't want it at all. It's fine. All right. Reading further. It makes sense for the next generation that the number of 0-year-olds equals the number of offspring from the 1-year-olds and 2-year-old females. Right, so we're trying to think of how many 0-year-olds or how many new whatevers there are next year. 0-year-old females are not mature enough to reproduce, and the okay, Grant writes some funny things in there, sure. And then assume that 1-year-old females have an average of 3 female offspring, and 2-year-olds have an average of 2 offspring. So we're saying the number of 0-year-olds next year is equal to 3 times the number of 1-year-olds this year, because each 1-year-old on average is producing 3 offspring, plus 2 times the number of 2-year-olds, because each 2-year-old is on average producing 2 offspring. So here's the matrix equation we're going to make for this. So remember how the matrix multiplication works. It's our row times our column. So we know that the number of 0-year-olds next year is going to be 0 times the number of 0-year-olds this year, because they don't reproduce, plus 3, not plus, there's no plus sign there, 3 times the number of 1-year-olds this year, plus 2 times the number of 2-year-olds this year. So our first row of this Leslie matrix is 0, 3, 2. And I always think of the first row of the Leslie matrix as how many 0-year-olds I'm going to get next year. My second row is going to be the number of 1-year-olds I get next year. Well, we know that 20% of the 0-year-olds survive to become 1-year-olds. So it's going to have a 0.2 right there. So that the 0.2 multiplies by the n0. And then a 0 and a 0. So the number of 1-year-olds next year is going to equal 0.2 times this year's 0-year-olds, and then 0 times this year's 1-year-olds plus 0 times this year's 2-year-olds, because none of those age categories become 1-year-olds next year. Finally, the number of 2-year-olds next year will be whatever fraction of 1-year-olds survived this year, which is going to be 70%. So it's going to be 0 times this year's 0-year-olds plus 70% times this year's 1-year-olds plus 0 times this year's 2-year-olds. So when I'm looking at this Leslie matrix, I'm thinking of the rows as kind of what I'm getting next year, and the columns are what this year is going into that. So this year, what's going into making next year's, oh my gosh, so let me say this the right way. No, I'm saying it the wrong way. That's the part my brain doesn't do as well, to be honest. Like I'm better thinking about the thing I already said. Yeah, I don't love thinking about it that way. I don't, yeah, right, sure. Sorry, I'm just trying to think about a way of describing what the columns are, but there's not really as good a description. I really am thinking about what the rows are doing. So I'm getting this row times this column, this row times this column, this row times this column to give me this column here. Questions so far? Okay. It's already, if you have questions, really don't hesitate to ask them. I feel like I'm doing an okay job explaining things, but please, 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 if you have questions, you should ask them. So let's look at what we've got going on further. Let's assume a starting population of 2,000 females of age 0, 800 females of age 1, and 200 females of age 2. And now we're asking the question, how many females are going to be in each category 1 year later? So we're essentially going to take our Leslie matrix that tells you how the population changes from year to year, and we're going to just write that down, 0, 3, 2, 0.2, 0, 0, 0, 0.70. And we're going to multiply that by the population vector they just described. We know that in year 0, there are 2,000 females of age 0. So it's 2,000 right there. And then there's going to be 800 females of age 1 and 200 females of age 2. So this here, this is our n of 0 vector. That's n0 of 0, n1 of 0, n2 of 0. And we're going to multiply this vector that's telling us all the populations at time 0 by the Leslie matrix to get all the populations 1 year later. Let's see what we get. So we're going to get 0 times 2,000 plus 3 times 800. Plus, I guess I could write it down. I'm not going to write 0 times 2,000. 3 times 800 plus 2 times 200. And then in the second row, it's going to be 0.2 times 2,000. Oh, there's something under, sorry, there's like there's a little thing under my paper there. Pardon me. And we don't need to write plus 0 plus 0. And in the third row, 0 times 2,000 plus 0.7 times 800 plus 0 times 200. And again, this makes sense based on what we've been saying, right? The number of 0-year-olds next year should be, well, they're each 1-year-old female should produce 3 offspring, so they're going to produce 2,400 offspring altogether. And each 2-year-old female should produce 2 offspring, so they'll produce 400 offspring. So we're going to get 2,400 plus 400, which is 2,800. And then 20% of the 2,000 0-year-olds survive to be 1 year old. So 20% of 2,000 is going to be 400. Right? Yeah, that's right. Like, right? Yeah, okay. And then finally, 70% of the 2-year-olds make it to be, sorry, of the 1-year-olds make it to be 2-year-olds, and 70% of 800 is 560. So that's our population 1 year out. And then this next question asks, okay, what about another year? How many females in each category are there in 2 years? Well, we're just going to multiply by this matrix again, right? If this matrix tells you how many you have every successive year, then we just have to keep multiplying by it to get the next year's population sizes. So we're going to do it again. All right. 0, 3, 2, 0.2, 0, 0, 0, 0.70 times my new 1-year-old matrix of 2,800, 400, and 560. So let's see what we get. So we get 0 times that plus 3 times 400 plus 2 times 560. And then we get 0.2 times 2,800. And we get 0.7 times 400. So multiplying it out, let's see, we get 1,200 plus 1,120 is 2,320. 0.2 times 2,800 should be 560. And 0.7 times 400 should be 280. I guess I can double check my numbers. I'm just doing Math in my head when I could be looking at answers. I don't think I'm making any mistakes, but it's good to, double check. Yep, all those numbers look right on. Cool. So again, I'll point out that this matrix here, this is called your Leslie matrix. The reason we're talking about this is because eventually the goal is is to be able to answer the question like, what are the sizes of each population is going to be like 20 years from now? And instead of multiplying by this matrix 20 times, there is a way to make that computation less terrible. Although usually we only do it for 2x2 matrices in this class, but still, that's what the idea we're working on is how to do this repeated matrix multiplication without having to actually do the repeated matrix multiplication. Okay. For now, though, we'll just continue looking at this handout. Let's look at the next page here. Ah, pages. Oh, good. I like this next question. So, for the following Leslie matrix, how many age classes are there? Well, it's a 4x4 matrix, so there should be 4 age classes. And if they don't say anything about what they are, we generally assume that the youngest age class is age 0, and then age 1, age 2, age 3 in this particular example. So there are 4 age classes. And we have ages 0, 1, 2, and 3. So I have a hard time reading this information off the matrix without writing down the multiplication. Like I can't see it unless I say, okay, I know I'm going to be multiplying by the number of 0-year-olds at time t, the number of 1-year-olds at time t, number of 2-year-olds at time t, the number of 3-year-olds at time t. So then when I'm asking what percentage of 2-year-olds survive to age 3, I'm essentially saying, okay, I want to see, well, what things are multiplying by the 2-year-olds? Well, I need something in the third column. And it's always kind of annoying that the numbers are off by 1, but like when you start at age 0, that's what you're kind of stuck with. So I know that my 2-year-olds are in the third row here. So I need this third column entry to be non-zero to be able to hit it. It's not this first row, right? Because this first row is all of this times all of this is going to give me the number of 0-year-olds next year, right? My first row, first column, that's the number of 0-year-olds next year. My second row, first column, is going to be the number of 1-year-olds next year. It's not what I asked. They're asking for the number of 2-year-olds make it to age 3. So I don't really want the third row with the first column. I want to know what's going on with the bottom row in my column here. So it's 0% of 0-year-olds make it to age 3 next year, right? You don't get any 3-year-olds from 0-year-olds this year. Same deal for 1-year-olds. But the 2-year-olds this year become 3-year-olds next year, and it looks like it's going to be 20% of them. So I have 0 times this plus 0 times that plus 0.2 times n2 plus 0 times n3. So the answer to this question is 20% of them. You might be better at this than I am as far as just looking at like I have to be like, okay, what's multiplying what here to figure out? So here's what I was trying to say earlier, which I think I can say a little bit better now. This row and this column. This row tells me what becomes 3-year-olds next year. And the columns tell me what things go into that. So here we have 0-year-olds, 1-year-olds, 2-year-olds, 3-year-olds going in. And we say, oh, 2-year-olds go in, and then for 3-year-olds coming out, we have 20% of 2-year-olds become 3-year-olds. That's kind of the way you could look at it if you wanted to. It's not really my favorite. But if you think about it like row 1, okay, 0-year-olds 1 times every 0-year-old becomes a 0-year-old next year. 2.5 1-year-olds become zero, each 1-year-old makes 2.5 0-year-olds for next year. Each 2-year-old makes 3 0-year-olds for next year. Each 3-year-old makes 1.5 on average 0-year-olds for next year. So that's kind of the way you can think about what the columns are versus what the rows are. The columns are kind of the inputs and the rows are the outputs. So along that same line, what is the average number of female offspring of a 1-year-old? Okay, so each 1-year-old is going to produce 2.5 offspring, because when we do the multiplication, right, next year's 0-year-old, the offspring, you're going to have 1 times this year's 0-year-old plus 2.5 times this year's 1-year-olds, plus 3 times this year's 2-year-olds, plus 1.5 times this year's 3-year-olds. So 2.5 on average. Because next year's 0-year-olds are equal to 1 times this year's 0-year-olds plus 2.5 times this year's 1-year-olds plus 3 times this year's 2-year-olds plus 1.5 times this year's 3-year-olds. It's all about matrix multiplication. Let's look at the next question. So here I think they want us to make the matrix. So let's read the question. Assume that a population is divided into 4 age classes again. So let's assume 0-year-olds, 1-year-olds, 2-year-olds, and 3-year-olds. And that 65% of the females age 0, 40% of the females age 1, and 30% of the females age 2 survive until the end of the next breeding season. It's kind of an interesting way of phrasing that. What we're really saying there is that 65% of 0-year-olds make it to age 1, and 40% of 1-year-olds make it to age 2, and 30% of 2-year-olds make it to age 3. That's what that's saying in a condensed way. And then assume further that the females age 1 have an average of 3 female offspring, females age 2 have an average of 7 female offspring, and females age 3 have an average of 4 offspring. We could write down a bunch of equations. We could say, okay, we know that the number of 0-year-olds next year is going to be, let's see, age 1s have 3 each, so 3 times the number of 1-year-olds. Age 2 have 0.7 each. That is a 0.7, yes. So 0.7 times the number of 2-year-olds. And females age 3 have an average of 4. So 4 times the number of 3-year-olds. We also know that the number of 1-year-olds next year, well, we know that 65% of 0-year-olds survive. So that's going to be 0.65 times the number of 0-year-olds from this year. 0-year-olds is hard to say. Sorry. And then the number of 2-year-olds next year should be, well, let's see, we said that 40% of the females age 1 survive to next year, so that's going to be 0.4. That's a 4, believe it or not, times n1. And then finally, 30% of females age 2 survive till next year, so the number of 3-year-olds next year will equal 0.3 times the number of 2-year-olds this year. Okay, we should be able to make the matrix out of all this. I don't think you necessarily have to do that. It's just what I'm doing to make it make sense in my head. So check out what I'm going to write here. For the number of 0-year-olds next year, I have 0 times 0-year-olds, and then 3 times 1-year-olds, 0.7 times 2-year-olds, 4 times 3-year-olds. For 1-year-olds next year, I have 0.65 times 0-year-olds, and then 0 of everything else. For 2-year-olds next year, I have 0 times the number of 0-year-olds, and then 0.4 times the 1-year-olds. 0, 0. And then for 3-year-olds next year, it's 0.3 times the number of 2-year-olds this year. What you see a lot of the time with these Leslie matrices, especially when it's population surviving till the next year, is this main diagonal being 0, all zeros, but right below the main diagonal, that's where all of your like who survived to next year pieces of data. Okay, then we have another question. If at time 0 the population consists of 1,500 0-year-olds, so let's make our vector here as we say it. So our population is starting off with 1,500 0-year-olds, 500 age 1, 250 age 2, and 50 age 3. We already found the Leslie matrix. Oh, I didn't. I answered the question kind of wrong. It's all right. I didn't draw the sketchy thing, which we haven't talked about yet. Not like sketchy, like that's kind of sketchy, but sketchy, like actually a sketch of a thing. So we'll do that in a minute here because I kind of jumped the gun. But all this question is asking us to do is to, again, do this matrix multiplication twice, which is not super exciting. So we could certainly do this multiplication twice. I don't think it's super necessary, so I'm going to say let's leave it to the reader. Leave the multiplication. As an exercise. But what I do want to point out is there was a diagram I was meant to have made that I kind of forgot about. So we can sketch a diagram for the number of 0-year-olds, 1-year-olds, 2-year-olds, and 3-year-olds. Oops, I can draw them on my finger as well. So here's what we're going to do. We're going to make little circles for each of the age categories. 0, 1, 2, 3. And then we draw arrows from one age category to another age category if some of that age category contributes to the other age category next year. So we know that 65% of 0-year-olds become 1-year-olds next year. So we would draw that. And 40% of 1-year-olds become 2-year-olds. And 30% of 2-year-olds become 3-year-olds. And every 1-year-old produces, on average, 3 offspring. And every 2-year-old, on average, produces 0.7 offspring. And every 3-year-old, on average, produces 4 offspring. That's how that matrix diagram would look. So this matrix diagram and this matrix are telling us the same information, just written in a very different way. And the idea was, if I had not jumped the gun, to go from this to this. And so you can kind of see that, oh yeah, what's going into the year 0 is everything that's in the top row there. What's going into year 1 is everything in the second row. What's going into 2-year-olds is everything in the third row. And what's going into 3-year-olds is everything in the fourth row. And then what's coming out is everything in the corresponding columns. So what's coming out of the first column is everything coming out of your 0, which is just 0.65. Everything coming out of your 1 is everything in your second column. The 0.4 going to the 2 and the 3 going to the 0, and so on, right? Everything coming out of 2 is everything in the third column. 0.7 going back to the 0-year-olds and 0.3 going onward to the 3-year-olds. So in and out. Columns tell you what's coming out of a thing. Rows tell you what's going into the next year's thing. It's kind of neat. I don't know. It's getting more like the biology part of this thing, but that's not the part I usually care about so much. Yeah. Sure. Let me pass this around while it's on my head. So 0.7, good question. Where did the 0.7 come from? Maybe I made a mistake. I think I might have made a mistake. No, okay, yeah. So it came from the last sentence here. Assume that females age 1 have an average of three female offspring. So that's where this 3 is coming from right here. And then assume that females age 2 have an average of 0.7 female offspring. I think that's a 0.7. There appears to be a dot there. So it's not 7, it is 0.7. So that's where that's coming from. All right. Other questions? All right. Turn the page. So one thing I would point out is these problems usually have a lot of words to read. You actually need to read them, right? We have to read them so we know what we're being kind of presented with and they are able to write down what they want to do. So let's read this. I want you all to construct the matrix diagram before I start writing stuff down. Well, let's read what we've got. Consider a population of women at risk of developing breast cancer. Each individual's health status can be in one of 3 states: healthy, early stage disease, or late stage disease. So we'll make circles because it's a matrix diagram, not the matrix itself. I learned my lesson. So in our matrix diagram, we're going to have 3 circles. We're going to have healthy, early stage, and late stage. Okay. So we know that each year, 0.3 of healthy women develop early stage, with the rest remaining healthy. So even though I said I wanted you to do this, I think we should do it together. So each year, 30% of healthy move over to early stage. So from healthy to early, we have 0.3 or 30%. The rest of the women that were healthy remain healthy, though. So the other 70% just stick around and stay healthy. Likewise, 68% of women with early stage disease recover through treatment, meaning they become healthy. So of the early stagers, 68% of them go back to healthy. 38% develop late stage. So none of them stay early stage. In this model, you don't get to stay early stage, apparently. Okay. So the other 32% become late stage. Finally, 15% of the women with late stage revert to early stage. And the rest remain in late stage. So the rest being the other 85%. I guess they didn't follow the directions. They didn't use lowercase letters. Oh, well. Not a big deal. Okay, so there's our matrix model. Matrix diagram, sorry, not matrix model. Now we're going to write the system of difference equations. So this word difference equations is just the next year versus this year. It's how many, it's your, how many, how do I want to write this? Your H sub t plus 1. So your healthy folks next year are going to be, or next iteration of time, right? Right. It does say each year, but really the time interval is going to be whatever, right? They can be months, weeks, seconds, depending on what we're talking about. So we know that next year, the healthy folks are going to be, well, 70% of this year's healthy folks are going to stay healthy. And then 68% of this year's early stage are going to revert to healthy. If you really wanted to, you could throw on a 0% of this year's late stage people are going to become healthy in one shot. It's not an option in this model here. For early stages next year, it's going to be, well, we know that 0.3 or 30% of the healthy people are going to become early. And then what else is going into the early? Early is not going into itself. So you have 0% of the early stage people stay early stage. And then of the late stage, 15% of them become early stage. So 0.15 times late stage. And then lastly, we have our late stagers next year. So none of the healthy people go straight from healthy to late stage. So it's 0 times the healthies plus 32% of the earlies become late stage. So, whoops, sorry. 0.32 times early. And thirdly, 85% of the late stagers stay late stagers. And really here, we've already kind of written the matrix. Oh, question, sorry. Also, if you have a question and I'm not looking up, just say, hey, James, I have a question. So, oh, thank you so much. I read that as a 0.3, not as a 0.3%. Good call. So it should actually be 0.03. Thank you so much. Which means this number is also incorrect, right? If 0.03, sorry, if I should say, if 0.3% become early stage, that means that 99.7% stay healthy. So that's not that, that's 0. I feel like I'm making a mistake somewhere. I think I'm off by a decimal place still, right? Let's do the smart thing. If you have 0.3%, you just move the decimal over twice, right? So I move it over twice, 1, 2. That should be 0.003, not 0.03. Sorry about that. Let's get it right the third time. Okay, 0.003, meaning the people who are healthy that stay healthy should be 0.997 or 99.7%. Sorry about that. Let's fix it. So this should be a 0.997 there. And that should be a 0.003. Good call. Thank you. The importance of reading things carefully. What I was about to say is, if we've written all this, you've already kind of written the matrix multiplication, right? What you've really written here, and it is good to be able to go back and forth between a system of equations and the matrix equations, which are the same thing, is this is really just your next time interval vector, ht plus 1, et plus 1, lt plus 1, equal to the coefficient matrix 0.997, 0.68, and 0 for the first row, and then 0.003, 0, and 0.15 for the second row, and 0.32 and 0.85 for the third row, times what would be the HT, ET, and LT over here. So these two things I've written, this system of equations and this system of equations are exactly the same. But now we can see the Leslie matrix right there. An interesting thing here, when you're talking about percentages of populations, your columns have to add up to 100% or 1, right? This first column is what happens to all the healthy people. Well, 100% of them better get dispersed to some place, either staying healthy or being early or being late. Similarly here, all 100% of the early stages have to get dispersed somewhere, and they do. 68% of them go back to healthy, 32% of them go on to late stage. And 100% of the late stagers have to go somewhere. 0 back to healthy, 15% back to early, 85% stay late stage. So specifically, we're talking about percentages of populations here. Each column has to add up to 100%, or 1 as a decimal. Okay, let's look at this last part here. Is this the last part? Oh, no, there's more. There's some more. How much time? Okay, what time is? So let's construct one of these matrix diagrams. So this is the part I've never been good at, to be honest. So the first row should be what's going into A. So what's going into A is 4 times C. So 0 times A, 0 times B, 4 times C. The second row should be what's going into B. 1 times A, 2 times B, 0 times C. The third row should be what's going into C. No A, 3B, no C. And yeah, right. I mean literally I have to think about multiply. If I multiply this by like AT, BT, CT, I'm gonna get my next AT is gonna be 4 times CT, cool. My next BT is gonna be 1 times AT plus 2 times BT, looks good. And my next C is gonna be 0 times A plus 3 times B plus 0 times C. That looks right on. So again, the idea of the what's going in being the rows, what's coming out being the columns is, I think, useful here. How much time have I got? Okay. So yeah. We'll skip B there. It might be harder the other direction, actually. Instead of starting with the diagram and writing the matrix, starting with the matrix and writing the diagram. Okay. So here I've got A and a B. So here's what I'm thinking of. I'm really thinking of multiplying this by some AT and BT and getting 1 AT plus 7 BT. That's my next A. And 4 AT plus 0 BT. That's my next A and B. So what's going into A should be A itself 1 time and 7 of B. What's going into B should be 4 of A and none of itself. So that should be our matrix diagram there. Again, what's going into A, a 1 and a 7. What's going into B, a 4 and a nothing. What's coming out of A, a 1 and a 4. What's coming out of B, a 7 and a nothing. Okay, seems reasonable. I'll leave you guys to do this one on your own. Okay, let's move on to the next thing. So I do want to mention this real quick here. Determine if the matrices A and B are inverses of each other. What does that even mean to be an inverse? Well, let me ask you a different question. What's the inverse of 5? 1/5. Now, I can be more specific. I should have really said, what's the multiplicative inverse of 5, which is 1/5. If I said the additive inverse, the answer would be -5, because -5 plus 5 is 0, whereas 1/5 times 5 is 1. But we are definitely talking about, and generally it's the case, when we talk about inverses, we mean multiplicatively. So to show that matrices are inverses, just like 5 times 1/5 is equal to 1, this matrix times this matrix, if they are inverses, should equal the matrix version of 1, which is the identity matrix. So let's see what we get. A times B is going to be 1, 5, 2, 7 times -7/3, 5/3, 2/3, -1/3. So let's check it out here. Oh boy, okay, I got fractions. So we get -7/3 plus 10/3. That's a good sign so far. Wow, that looks terrible, James. And then this with this is going to be 5/3 minus 5/3. And then second row, first column is going to be -14/3 plus 14/3. And then second row, second column is 10/3 minus 7/3. And I'm looking pretty pleased about that because that's exactly equal to 1, 0, 0, 1. So A and B are inverses of each other because when you multiply them together, you get the identity. And atypically, when matrices are inverses of each other, it doesn't matter which order you multiply them in. So I could have done A times B. I also could have done B times A, and I would, in this case, get the same result. That's really not generally true, but it is true if matrices are inverses of each other. So note here that if matrix A is invertible, A times A inverse is equal to A inverse times A is equal to the identity matrix. So in this special case, order of multiplication doesn't actually matter. Let's look at this A and B over here. So if we multiply this A times this B, 0, 1, 3, 2 times 2, 3, 1, 0. I have a bad feeling about this one. Let's check it out. A bad feeling I don't have very much room. So the 0, 1 with 2, 1 is going to give me 1. 0, 1 with 3, 0 is 0 plus 0, which is 0. But then 3 times 2 plus 2 times 1 is 6 plus 2, which is 8. And 3 times 3 plus 2 times 0 is 9. No dice. This is not the identity matrix. So these matrices are not inverses of each other. I don't want to do A and B because it seems like a pain in the butt, but I do want to talk about this last one here because given almost any 2 by 2 matrix, we can find its inverse. So here's how you find the inverse of a 2 by 2 matrix. I'll start with just the general formula. So if the matrix A is equal to A, B, C, D, then the inverse matrix, A inverse, is equal to the following. It's 1 divided by a quantity that you will come to know as the determinant of the matrix A. It's A times D minus B times C, multiplied by, for a 2 by, this is how it works for a 2 by 2 matrix. For larger matrices, it is a much more complicated process. For 2 by 2s, it's really, really easy. You just interchange the diagonal entries. So A and D switch places. Make sure your D and your A look different. And then the off-diagonal entries, B and C, they stay where they are, but they change signs. So instead of having B and C, you have negative B and negative C. And that matrix is the inverse of A. And so this matrix exists as long as or if AD minus BC does not equal 0. Because if that was 0, then we'd be dividing by 0 and then it wouldn't work. So what this really means is that not every matrix is invertible. That quantity called the determinant of A has to be not equal to 0 for a matrix to have an inverse. In this case, that's going to be true. Here, the determinant of A is 2 times 4 minus 1 times 5, which is 8 minus 5, which is 3, which is not 0. So the inverse exists because the determinant is not 0. And then the way we find the inverse is, well, it's not too bad. It's going to be 1 divided by that number, multiplied by, switch the 2 and the 4, And then the off diagonal entries change their sign from 1 to -1 and 5 to -5. And you can either leave it like this, or if you care to, you can distribute the 1/3 and say the matrix is 4/3, -1/3, -5/3, +2/3. And you can check for yourself, if you multiply this matrix by this matrix in either order, you will get the 2 by 2 identity matrix. All right, that seems like a good stopping place, even though it's only 158. I'll live. See, and you guys all have a midterm on, well, I should say, those of you that didn't have a midterm today have a midterm on Monday of next week, right? Okay. I'll see you all on Wednesday. I'll try to post some sort of practice something or other. Thank you.